Hello, welcome back as we start our journey. The first formal topic, I wouldn't say formal, sorry, I promised informal yesterday. We are going to start linear algebra and then get into other aspects like optimization or machine learning, whatever. When we are talking about linear algebra, you will hear first concept is that of a vector space. So if you take any linear algebra book, standard books taught in colleges and universities in India, the first, even when I was in college, then I was also learned, okay, you open a book, they will start with something like a vector space, there's a field and blah blah stuff. There are certain rules that the objects of that set should follow, and there are two kinds of things and so on and so forth, and various examples of so-called vector spaces and good blah blah stuff, and then all the results. But why you need to think of such a thing? My issue is to deal with that. Other things you can read in books. So what is a vector and why this terminology vector space has come? When do you think you had first heard about the term vector? If I remember correctly, it was in a physics course. When we first heard about displacement, we heard about velocity, we heard about acceleration, force. So all these are vectors, are quantities which has both magnitude and direction. But from a mathematical point of view, the concretization of the idea comes when you start looking at geometrical vectors. That's what you do in your high school. You talk about geometrical vectors. A geometrical vector, to start with, is a idea that you built up in the two-dimensional plane. So two-dimensional plane means it consists of two axes, the x-axis and the y-axis, the vertical, and the x-axis is the horizontal one, the vertical is the y-axis. Now take O as the origin. Then take any point other than the origin and join it with a straight line. Then put an arrow on the top. Then this point where the line has ended is called the tip of the vector, and O is called the origin of the vector. It's like a straight line, origin and destination pair. Now what happens? So this has a magnitude. This line, its length you can measure, and it has a direction. So if you take any other point, any other point on this plane and join it with this origin, it will have a different direction, right? Length can also be different. Now this tip, any point on the two-dimensional plane, as our Cartesian geometry in high school teaches us, can be represented by two real numbers called the coordinates of the points, right? Now, so a vector v, which we call this as a vector v, this has a representation in terms of two real numbers. So a vector in a two-dimensional plane can be represented as a collection of two real numbers, the coordinates. So which we write as v is equal to xy, which you can now see. V is equal to xy. Now, if you draw the thing in 3 dimension, when you have the z-axis or the z-axis, if you want to call it, height axis, length, breadth and height, then you have another coordinate x, y, z or x, y, z to represent the point. So then the vector is represented by x, y, z. So if you want to move beyond three dimensions, you can talk about Rn. You can talk about n-dimensional vectors, where each vector is now represented by n real numbers. So each of these x1, x2, xn is a real number, which you can see very well. Okay, so this is the model of a vector space. Okay, now this is the basic model of vector space. Why we call it space? Because we know this two-dimensional plane is sometimes called a two-dimensional space because it's a collection of points, and each point is represented by a coordinate. But each coordinate is also now represented as a vector, can be identified with a vector. So we can call it as a vector space too. And that name had stayed on. So this Rn where n could be 1, 2, 3, 4, 5, 6, 7, whatever you want, is the basic model of the idea of a vector space. And here, because geometry plays a fundamental role. Now R1, when n equal to 1, is the number, is a thing which everyone knows, which is the real line, set of reals. Okay. Now, by convention, a vector is always represented by a column vector. Means you write down the coordinates in a column, not in a row. Though it is sometimes used as row, written in rows also, but in general you write them in columns. V is x1, x2, xn. Okay. Now, usually elements of the real line R is denoted by alpha, beta, gamma, and that of a vector we denote as V, W, A, B, C, P, Q, whatever. In the book by Gilbert Strang, let me again bring back Gilbert Strang's book, this one, right? And let me read the first line of the first chapter, if I am not wrong. The first line of the first chapter, I guess. And he says, the heart of linear algebra is in two operations, both with vectors. Now, what are those two operations which are at the heart of linear algebra? And these are called the operations of additions and scalar multiplication. Means how will you add two vectors? How will you multiply a real number with a vector? So these are the two operations which lies at the heart of linear algebra, and the whole linear algebra, in fact a lot of mathematics actually, can be built on these two operations. And that idea is precisely what we discuss. Now when you are in Rn, what do you mean by addition of two vectors? What is the meaning of that? We will give you a geometrical picture also, but let us first be algebraic, right? Because beyond 3 dimensions you cannot see. But can we use those geometrical ideas beyond the geometrical ideas that we have, the common geometrical ideas that we have for R2 and R3, can they be brought beyond R3, means n equal to 3? So then algebraic viewpoint plays a much bigger role. So algebra is actually a machinery. That is why it is called linear algebra, because ultimately you are looking beyond the geometrical dimensions. You are looking beyond 3 dimensions, because beyond 3 dimensions is what matters. A lot of things happen beyond 3 dimensions. For example, in special relativity, Einstein considered a space-time continuum where he considered the time variable along with the 3 space variable t, x, y, z. T is the time variable, x, y, z are the space coordinates, length, breadth, height. And this is called a 4 vector by physicists. And so obviously it is in 4 dimensions. So when it goes beyond our geometrical visualization, 3 dimensions, it is very important that algebra takes the central role. So that is why we call it linear algebra, and that is what we are showing, that first we give an algebraic definition of things, and then we try to see what we have learned at a lower dimension, 2 or 3. My drawings will be all of 2 dimensions. 3 dimensions might be very complicated to understand just by looking at somebody telling something on the video. So let's see what is vector addition. So suppose I have 2 vectors, v and w. V is the one which has coordinates x1, x2, xn. So it represents a point P, say, with a coordinate x1, x2, xn. And w is a vector which represents another vector with coordinates y1, y2, yn. Then v plus w is again a vector in Rn whose first coordinate is x1 plus y1, that is sum of the first 2 coordinates, this x1 and y1, and so on and so forth. The second one is x2 plus y2, and so the last one is xn plus yn. A simple operation. Nobody has to be facing any problem with these kind of simple operations. Now comes the operation of scalar multiplication. You take any real number, Don't take a complex number even if you see, but you can try out with a complex number. See, the idea behind these two is that when you add two vectors in Rn, the resulting vector has to be in Rn. It cannot be in some other esoteric place. Then only your algebraic operations would become meaningful. So when you make a scalar multiplication of vector, this also has to return a vector in Rn. It cannot go to some esoteric space. That is why the alpha that you consider, the scalars are elements in the real line. This alpha that you consider cannot be anything else. You cannot say, okay, let me have some fun with complex numbers. Then you go to a different space. You do not remain in Rn. You go to some space called Cn, right? Which we are not talking about. We will try not to get into all these complications. We will be more or less in Rn, where optimizers can play their games, engineers can play their games, and so on. So what you see here, you have a scalar alpha element of R and a V in Rn which has coordinates, say V1, V2, Vn, or for just to make a difference I am writing the V as a coordinate V1, V2, Vn. So this alpha V, this alpha V operation that you see here, this alpha V operation is nothing but multiplying every coordinate of V with this real number alpha. So the new vector alpha V has a coordinate is a vector whose coordinates are alpha V1, alpha V2, alpha Vn. So here is an example of a vector. So you know if you put alpha equal to 2, what would happen? Now what does it mean geometrically, these ideas? That is of great significance to understand what does it mean geometrically. Let us first look at addition. This is an idea which is known to everyone, the parallelogram law of addition. So here you see the vector V, here you see the vector VW. What you draw is out from the tip of vector V, you draw a line parallel to vector W and of the same length, and from the tip of W you draw a line parallel to V and of the same length as V, and wherever they intersect, join that point with the origin O, and that point would be giving you the vector V plus W, and whose coordinates would be, as you see, the addition of the coordinates, respective coordinates of V and W. Now, interestingly enough, where did this vector V, this idea of vector addition come from? Where did it first originate? This interesting part is that this idea was embedded in the Principia of Newton. Newton writes after his Newton's laws that, okay, if you have if there is an object on which two vectors or two forces are acting, say in a perpendicular direction, two forces are perpendicular to one another, then the object will not go in the direction of any individual force but along some other trajectory, which is actually the addition of these two forces. So what you do at home, you take a marble or any ping pong ball, take two dot pens, a similar type, and hit that at the same time, the ball, perpendicularly. Just put one pen in this hand, put one pen in the another hand, and just hit it simultaneously. You will see the ball will shoot off like this. It will not go in this direction or this direction. It will not go either horizontally or perpendicularly. It will shoot off in a 45-degree direction. And that's actually the addition of these two forces, confirming that forces are also vectors. So, in the book by Arnold Sommerfeld, a great physicist who has contributions in quantum mechanics, he has a book on classical mechanics where he says that this particular law, which is actually addition of vectors, should be called the fourth law of motion. So, addition of vectors, this idea, though not very clearly formulated, was actually known to Newton. So now comes scalar multiplication. So if alpha is greater than 0, then scalar multiplication actually means that I am either pulling the vector or shrinking the vector. So when alpha is greater than 0, greater than or equal to 0, then alpha v means the new vector alpha v is in the same direction as v, but if alpha is bigger than 0, its length is bigger than v, it is alpha times the length of v. If it is less than, alpha is strictly bigger than 1, then it is alpha times v. and if it is alpha is strictly less than 1, then I have shrunk the vector. So if alpha is 2/3, then the length of the new vector is 2/3 of the old vector. But if alpha is negative, then the direction of the vector changes. So if v is in a given direction, the minus alpha v means alpha is say negative number, then alpha v is in the opposite direction. So these are the things that you have to keep in mind. I would like you to just, for a sake of homework, figure out how do you prove using simple Euclid's geometry, school geometry, that if we draw a parallelogram like this, the way we said, that this point would be really the sum of the individual coordinates. Now we come to one of the most critical idea in linear algebra, the notion of a basis. Basis means from very few number of elements, I can create to all the infinite number of elements that make up the vector space. For example, and this viewpoint was possible because of these two operations of addition and scalar multiplication. That is why possibly Gilbert-Stein writes that these two operations lie at the heart of linear algebra. These are the two operations which are lying at the heart of linear algebra. That is what makes the subject move. So suppose now I have a vector v whose coordinates is x and y. But if you observe that I can write xy as this number, real number x, scalar multiplied with a vector 1, 0, plus real number y, scalar multiplied with a vector y, 0. Because if I multiply x with 1, 0, I get x, 0. And if I multiply y with 0, 1, I get 0, y. If I add them, I get x on the top and y at the bottom. So I get back this one. Now this is true for any xy. Any point x has a coordinate, say xy. Any point which has a coordinate, any coordinate, 2, 3, 4, 5, I can always write it like this. So by using these two vectors 0 and 1 and putting any real number here, I am actually generating any point in R2. So if I put 2, 3 here, I have generated the point 2, 3. So in this way I can generate the whole space. So I say that these two vectors 1, 0 and 0, 1 span the set R2. They spans the set R2. Do you see it? I call it that it spans the set R2. Okay, right. So these two vectors are called the basis of R2. This is the base on which R2 is built. It's like a foundation of a house. You know, you must have a foundation on which the house is built. So this is a kind of foundation. This is the foundation of vector space, of this vector space R2. But interestingly enough, this basis is called the standard basis because this is the most easiest way which you can decompose a coordinate. But that doesn't mean that this is the only basis. Mind you, this is not the only basis, because if you look at it, if I rotate the coordinates and have x dash y dash, then a point P which was having the coordinates xy in our standard this system xy, we will have a different coordinate x dash y dash in the new system, in the rotated coordinate frame. When I have rotated, my new frame is this. New Cartesian system is this one. Then along these new x dash and y dash, draw two perpendicular vectors. They are 1, 0, 0, 1, whatever be the vector. Then with these two vectors again you can generate the whole space. So the basis need not be unique. There can be many such bases. We will come into a more deeper ideas of what basis is and what are their structures, what are their properties. But that is what I want to say, that this is the most easiest basis. That is, it's called the standard basis or canonical or natural. Canonical means natural. But this doesn't mean that this is unique. It can change. So it is all about the frame of reference. From which point of view you're looking at a point. So you can keep on changing your coordinate system, right? Instead of having in this way, you could have had a coordinate system in this way. This could be the position of the y-axis. Here this could be the position of the x-axis. So the viewpoint changes. The viewpoint changes, but the basic laws of linear algebras remain. That's the key idea. Even if you change the coordinate, the basic idea that there will be always a basis. Even in the new coordinate system, you can find a basis. So given a space, there are many ways I can find a basis. In fact, there are infinitely possible bases. So you can choose to work with one of them. And you choose a basis according to your need. So that is the key idea, that the appearances change, but laws of linear algebra survive. Now you might be asking, okay, you did addition, you did multiplication, scalar multiplication. But what about multiplying two vectors? What is the meaning of that? So you meet two vectors in Rn, each having n coordinates. What is the meaning of multiplying these vectors? Is there any meaning of multiplying these vectors? Now I say, okay, I only know about multiplication of real numbers. Can that idea be brought into the vectorial zone? So if I have a V which has n coordinates x1, x2, xn, and if I have a W which has another n coordinates y1, y2, yn, I can say, okay, I can multiply the first coordinate of V with the first coordinate of W. So x1 into y1. Then I do with the same with the second coordinates. Okay, so I have a bunch of multiplications. What I do with them? One simple and powerful idea is to add these values. So x1 into y1 plus x2 into y2 plus xn into yn. This is what is called a dot product, and that's what I'm trying to show you now. That is what is called a dot product, right? So here you have two vectors, x1, x2, xn, and w is y1, y2, yn, and this is v and this is w, and then v in dot w is x1 into y1 plus x plus dot 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 xn into yn. You see, so it's a very simple thing. There is an alternative symbol which mathematicians love a lot. You write it. This is called the inner product. Sometimes dot product is also called inner product. Now, my friends, so here is an example. So we have solved the vectors in R2. See, there you must have observed there is some symbol discrepancy. You might say that whenever you are talking about vectors in R2, you are putting this arrow. This is what we have learned in school, that when you have a vector, you put an arrow to say that this is something which has a direction. But when you are coming into the more algebraic framework of higher dimensions, we shun the arrow because we understand that this is the symbol we'll use for vectors. So we will have this understanding between us, and that is why we will work. And this is old habits die hard. So in 2 dimension, you will find me doing these things. Even if you don't like it, just tolerate this a bit. So now here you have the vector 1, 1 and 1, 0. Then v dot w is 0. V dot w is 1. If v dot w is 0, then we call the vectors v perpendicular to the vector w. So for example, you take this vector 1, 0, which is usually called E1, and it is, if you call it as E2 is 0, 1, then E1 dot E2 is 0. So these vectors are perpendicular, even if you have seen in the last slide that these vectors are perpendicular, because they are talking about that these are represented by the coordinates 1, 0 and 0, 1, right? So these coordinates which are representing the vectors 1, 0 and 0, 1, the 1, 0 is called E1 and 0, 1 is called E2. Now, how do you talk about the basis in Rn? The basis in Rn is done in a similar way. And the standard basis, finding the standard basis is again the same story. So you have a vector, say v, which has x1, x2, xn, and this has coordinates, right? And you have, sometimes some books will write x is equal to x1, x2, xn. So many cases people write x equal to x1, x2, xn, y equal to y1, y2, yn. But this might confuse people. So I am making a very clear distinction that I will always talk about a vector as a vector v and their coordinates in terms of these real numbers is x1, x2, xn, xs or whatever. So here, suppose there is a vector v with coordinates x1, x2, xn, then again you can write x1 into 1, 0, 0, 0, which we call e1, x2 into 0 1 means the if I take the ith vector coordinate xi, then I'll write xi into a vector whose all coordinates are 0 except the ith coordinate which is 1. So that is why. So this is called E1, E2, EI dot 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 En. So this E1, E2, En, they form what is called the basis of Rn or the standard basis of Rn. Right? So again, I want to remind you that Rn can have more than one basis, infinite number of bases. A very important concept is called the norm of a vector or length. And here, given in R2, if I have a vector P given by the coordinate xy, it is very simple to calculate the length by using the Pythagoras theorem. So OP, this OPD is a triangle, a right angle triangle, and this is nothing but x, the length of the x coordinate, and this is y, the y coordinate value. So R is nothing but root over x square plus y square, the standard Pythagoras theorem that you have used in school. This length is called the, when you are talking in higher dimension, you are calling it as the norm of the vector v. And that is nothing but root over x1 square plus x2 square plus dot 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 xn square. Actually, it is nothing but the distance of this coordinate point xy from the origin, and that is the length of the vector. So norm of v means the length of v. If you give a little thought, then you will see that the norm of v square can be written as the dot product of v with itself. Because if v is x1, x2, xn, and then if you do v dot v, you do x1 into x1, x2 into x2, and hence x1 square plus x2 square plus xn square, which is nothing but the square of the norm. See, this is nothing but an extension of Pythagoras theorem. You know how to calculate things in R3, the three-dimensional space. So you will know this in n-dimensional space. So we end it here today. Tomorrow we are going to talk about properties of the norm, and we are going to introduce, just by knowing about the properties of the norm and the knowing about this idea of inner product, we can talk about a very important inequality, one of the most famous inequalities in all of mathematics, the Cauchy-Schwarz inequality. And you will see, I'll give a proof from the book of Corner, and it would be just wonderful. It will be step by step, and you will see, you will enjoy how powerful, very simple ideas of mathematics are. So I hope you enjoyed with me today, and do put your comments. If there are certain issues, please ask me. Maybe I'll be able to answer you in the comment box. Thank you very much. Have a good evening.